afternoon I wish to our speaker, Dr. Arni Munira Markom, and to all the participants that are joining us today. I am Dr. Nadiah Husseini, Zainol Abidin. I am affiliated with IEEE Photonics Malaysia as a committee member, and I'm also the Vice Chair of IEEE Young Professionals Malaysia. The Photonics Lecture Series 2021 is held in collaboration with both IEEE Young Professionals Malaysia and also IEEE Photonics Malaysia. For this year, we have successfully hosted 3 speakers to talk about their research, and the talk by Dr. Arni today will be our 4th for this year. We are expecting 3 more speakers for this year. It has been very exciting for us learning all these latest technologies in photonics done by esteemed scientists, and I hope everyone will continue to support us in this series. If you would like to refer back to any of the talks that was held before, you may do so by finding IEEE Photonics Malaysia on YouTube. Okay, so before we start with Dr. Arni's talk, I would like to introduce her first so everyone's on the same page. So Dr. Arni Munira binti Markom is a senior lecturer at the School of Electrical Engineering, University Technology Mara, who had received her doctorate degree in electronics from University Malaya in 2016. Over the past 2 years, she had received notable rewards, including Most Diamond Innovator and Most Promising Academician from the Faculty of Engineering UITM in 2019, the Aspiring Innovator Award at the 9th International Innovation, Invention and Design Competition 2020, and Best Writer in State Academic Award in 2021. Her research focuses on fiber lasers, fiber sensors and amplifiers, not forgetting Arduino and IoT devices as well. Please welcome Dr. Arni to give her talk entitled Zirconia Erbium-doped Fiber Towards Dark Pulse Laser Generation. That was a mouthful. Dr. Arni, the floor is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good evening to everyone. Okay, thank you to our moderator, Dr. Nadiah, for the introduce and the invitation. And also, I would like to take this opportunity to express my gratitude and appreciation to Dr. Yasmin, Professor Madya, Dr. Siti Barirah. I saw her just now. And then, of course, IEEE Photonic Malaysia and IEEE Young Professional for this invitation series, Photonic series. Okay, Photonic lecture series with my topic. Okay, I just want to share my slide right now. Okay, can you see my slide?
Yes.
Okay, thank you. So, my topic for this evening is about Zirconia Erbium-doped fiber towards dark pulse laser generation. Okay, before that, I would like to break the ice. So my name is Dr. Arni Munira binti Markom. You can call me Arni. My place of birth in Batu Pahat, Johor. Yes, I am Johorian. I'm still younger, 37, and I'm married with 5 kids already. So the academic background is introduced by moderator. Okay, I have bachelor degree in electrical electronic engineering from UTM on 2007. My master in microelectronic UKM 2009, and the last one my PhD in electronics engineering photonics in University Malaya on last 2016. Okay, so my current designation is senior lecturer in School of Electrical Engineering, College of Engineering, UITM Johor. So now our UITM doesn't have any more Faculty of Electrical Engineering. Okay, so we changed to School of Electrical Engineering, and all engineering combined under College of Engineering. Just for your information. Okay, and then I will go to scope of sharing session. So first I will introduce the pulse fiber laser, Zirconia erbium-doped fiber, important parameter in the pulse fiber laser, and then we will go to bright pulse first, fiber laser, and then switchable bright to dark pulse, and then we will go to dark pulse by using graphene oxide, saturable absorber, and dark pulse with black phosphorus saturable absorber. And then a little bit discussion about this pulse fiber laser. And then first, I would like to introduce a pulse fiber laser. So maybe most of you already know the fiber laser, and maybe some of you are not. So I will explain a brief explanation about what is fiber laser. So actually, fiber laser is a laser where a device, that device is we call as fiber. Okay, or we call as a, sometimes we call as a gain medium or active medium. So it can perform stimulated emission process, the optical amplification of laser. Okay, so it will emit a coherent light, that means same phase, same magnitude, and same frequency. Okay, so what is the fiber laser application where we will use the fiber laser? So uh, normally nowadays there are many and various application. Okay, for example, military. So in military they will use for radar, for imaging or weapon. Okay, like Star Wars, right, may the force be with you. Okay, the weapon, and then the beauty and skin. Okay, previously they are using a lot of for tattoo, they are very popular for tattoos removing. Okay, but now I saw that they are using for hair removing and also scar removing. Okay, especially for dermatology. And then also fiber laser can be used for communication, dental laser treatment. Okay, for scaling. Now scaling also use by using laser. And last of course for medical application, like laser surgery treatment. Okay, previously I saw Dr. Amalina Bakri, our genius in UK. She performed a very large laser machine to cutting human body. Okay, that one is to replace a scalpel. Okay, so by using fiber laser, it can cut human body. Okay, that one is very safe. Okay, fiber laser is very safe. Okay, I mean very fast and efficient enough to cut human body without left any trace. Okay, like scalpel, it can left some amount of heat, okay, into the body, but laser won't. Okay, so that one is very advantageous in the recent laser technology. And then what is dark pulse? Okay, dark pulse is in as a researcher, they said a pulse with a dip in the intensity of laser emission. As me, to be short, dark pulse is pulse going down. Okay, normally as you can see, a heartbeat, the pulse will be going up, right? In the movie, right? But dark pulse, the pulse is going down. Okay, I remember at the first time we saw the dark pulse, we don't know what is this. Some of my friend also said, oh, maybe the my configuration is backward. Okay, reverse. But no, actually that one is a dark pulse. Okay, and then what is the advantages and disadvantages dark pulse compared to bright pulse? Okay, at first advantages, actually dark pulse is less interference compared to bright pulse, and it has excellent stability in the presence of noise. Okay, however, the disadvantages, it less discovered due to very difficult to create this dark pulse. Okay, so less discovered, so less people talk about this. But nowadays, it's already a lot of people can create the dark pulse. Okay, then we introduce you what type of the fiber that I used during my research. So I'm using Zirconia Erbium-doped fiber. Okay, this fiber is fabricated using modified chemical vapor deposition (MCVD) process. Okay, during my PhD, I'm not fabricate this fiber. This fiber is fabricated in India by Professor Dr. Mukul. Okay, he is a collaborator with my supervisor, Professor Sulaiman Wadi Harun in University Malaya. Okay, so I'm using this fiber to generate various type of amplifier and fiber laser. Okay, so as you can see my slide, I show you the difference between zirconia erbium-doped fiber and erbium-doped fiber. Two different. Okay, erbium-doped fiber is a commercial one, established. Okay, like our Unify using erbium-doped fiber. Okay, however, why we need zirconia erbium-doped fiber instead of erbium-doped fiber? Okay, the reason is erbium-doped fiber is already stuck at 2,200 ppm concentration. Okay, if they want to improve the concentration, they need a very complex configuration, experiment configuration to increase the concentration. Okay, however, so that Erbium, that Erbium is the reactive, okay, to develop the amplification, to develop the laser. Okay, Zirconia cannot. However, Zirconia is the material that boosts up the erbium doped fiber to higher concentration level. Okay, so when they fabricate zirconia together in the erbium doped fiber, so the erbium doped fiber concentration going up to 400 ppm compared to normal is only 220 2200 ppm. Okay, and the difference also in the absorption rate. Okay, the absorption rate is quite high, 80 decibel per meter at 980 nanometer, whereas erbium doped fiber only 23. Okay, so erbium doped concentration is important to generate more optical amplifier optical gain. Okay, yeah, and then absorption rate is quite high so that it can generate at a longer wavelength. Okay, like erbium doped fiber, they generate the laser in the C band. However, zirconia can go to L band and extended L band. Okay, very long transmission network. And then other properties like fiber diameter, refractive index difference, and numerical aperture is like quite similar. So they different in only for the concentration and the absorption rate. Okay, and then okay, as you can see at the picture, at the top one is that one is the erbium. Below one is the zirconia. Okay, zirconia normally we are using for what for beauty what like ring, diamond, something like that. The jewel jewel. Okay, and then we go to important parameter of pulse fiber laser. So in this sharing session, I only talk about three important parameter. So the first one is repetition rate. This is a frequency, so it would be in hertz. Okay, the higher frequency much better for pulse fiber laser. The second one is pulse width, as for time actually. So the narrow pulse, the high speed fiber laser. Okay, the narrow pulse, the higher speed fiber laser. And the third one is optical signal to noise ratio, or SNR, okay, in decibel. So this one is important to define the stability of pulse fiber laser, either in bright pulse or dark pulse. Okay, so I will talk about these three important parameter only for next next slide. Okay. Okay, so first we go to bright or normal pulse. Okay, as you can see, this is soliton lock pulse using single wall carbon nanotube saturable absorber. Okay, this is the left one. This is the experiment configuration. Okay, the pump used is pump 980 nanometer. Okay, because before this I show you the absorption rate 80 dB at 980 nanometer, and also the erbium doped fiber at 980 nanometer. That's why the most suitable pump is pump 980 nanometer. And then if we go to wavelength division multiplexer, and then we go to zirconia fiber. So this is uh, the place where the optical amplification will be happen. Okay, so sometimes we call as a gain medium or active medium. Okay, and then it will generate the laser here. And then if we go to polarization controller to control the polarization, and then go to coupler. So the coupler will go to oscilloscope for measure the bright or dark pulse, and optical spectrum analyzer to measure the optical spectrum. Okay, and then before that they will go to saturable observer. Okay, and you can see in the middle picture I show you a tiny thin BP. BP is black phosphorus. This is an just example how we put saturable absorber in the pigtail. Okay, just put and set it by using index gel matching, index matching gel. Okay, and then it will sandwich by two coupler, and then we go to isolator to make sure one direction only, and then going rotate again. So this is what we call as ring cavity. Okay, it will go round and round. Okay, so okay, and the right side, this is optical spectrum. Okay, as you can just see, this is a soliton with scaly sideband. Okay, the right and height peak we call as a Kelly sideband. Okay, okay. As here for information, modulation depth in this saturable absorber is 2.8 percentage. Okay, this modulation depth is important. Saturable absorber. Okay, I tell you saturable absorber. The two important component to create fiber laser is zirconia fiber and saturable absorber to create the fiber laser. Okay, zirconia fiber saturable absorber. The function is it will absorb all the low intensity light. Okay, low intensity light that we don't want to use, it will absorb, and it will release only the high intensity light of laser. Okay, and it also depend on the modulation depth. Okay, it must large enough to perform a strong pulse shape. Okay, this modulation depth is the reason a pulse shaping, okay, either the bright or dark pulse will shape, and then it also allow the self-starting pulse. Okay, so this modulation depth of single wall CNT is strong enough to create soliton modlock, but not strong enough to create dark pulse. Okay. So here as you can see, this is the result of the single wall carbon nanotube. Okay, this is bright pass going up and clean and neat, right? Okay, and then the right side is the autocorrector measurement. So the pulse width is about, this is pulse width. Pulse width is about 770 femtosecond. So this is very narrow. Okay, and then the repetition rate is also high, it's about 17.7 megahertz, and the radio frequency peak is about 37.4 dB. Okay, radio frequency is the OSNR, optical signal to noise. Okay, normally in the research, RF frequency must be up than 30 dB, 30 decibel. Okay, to be considered is stable enough for the fiber laser in the configuration. So this is the normal and bright pulse. And then we go to switchable bright dark pulse. Okay, as you can see in the configuration, I plug off the saturable absorber. Okay, before this, we have saturable here. Okay, but here I plug off the saturable absorber, and this configuration is called nonlinear polarization rotation. Okay, so it depends only on the rotation in the in the configuration. Okay, so this is the result of optical spectrum by optical spectrum analyzer. Okay, as you can see, it switch bright to dark, dark to bright. Okay, pump power at 70 milliwatt. Okay, the bright is the red one, and the dark pulse is in the blue one. Okay, and then the modulation depth for this this is wrong. This is dosa. I put the wrong in the wrong slide. Okay. Ignore the because this for this nonlinear polarization and rotation for NPR, there is no modulation depth because we are not using any saturable absorber. So still we can treat the laser without using saturable absorber. Okay. So the result here, as you can see, that one is not very neat and clean, right? It will going up, and then at the below one is the pulse, okay, going down, okay, because and then the repetition rate both are same, 14.1 megahertz, okay, quite high. And then the RF also 33 dB. Okay, as I said before, 30 up then 30 is considered stable. So it's only 33, so not stable enough. Okay, stable but not strong enough. Okay, that's why it switched back to dark to bright. Okay, and then the pulse width is about 27 nanosecond. Okay, nanosecond here is quite large, not narrow. Okay, we consider that's why we cannot measure by using autocorrector. Autocorrector only can measure femto to picosecond, pico to femtosecond only. So there is no autocorrection result for this. Okay, so we just measured manually the pulse width. Okay, by right, after two experiment here, okay, first I put CNT, carbon nanotube, with low modulation depth, and then we plug off the saturable, and then I try to put graphene oxide saturable oscillator. Okay, so for GOSA, uh, the modulation depth of GOSA is about 3.5%. Okay, higher than CNT. So as you can see, I put saturable absorber after zirconia fiber, and I add some single mode fiber, 200 meter. Okay, single mode fiber here is to increase the non-linearity inside the cavity, inside the configuration. Okay, what is important for non-linearity? So actually, non-linearity is to explain non-linear response. Okay, to the optical properties, especially for light intensity, like laser. Okay, such as the frequency effect. Effect the non-linearity is non-linearity will affect to frequency, pulse width, polarization, and phase in the configuration. So here, as you can see, at the 54 milliwatts is already show one single lasing here, and the dark pass at the right side. And then when three multi wavelength, so the dark pass is quite neat, and it become neat and clean when five lasing multi wavelength is performed. Okay, the repetition rate for this is about 1 megahertz. Okay, this is smaller than previously than CNT, however still in mode locking. Okay, this one is pulse width. Okay, as I said, our autocorrector only can measure the narrow pulse width. So this is considered narrow, 3.43 picosecond. Okay, I able to capture the autocorrector measurement, and this one is radio frequency RF frequency analyzer actually, OSNR 43.08 dB. Okay, as you can see, the OSNR is also large. Okay, that's why our dark pass here is quite stable when 5 lasing is appear. Okay, and then okay, this is modulation. Okay, again I put the wrong modulation tab here. This is BPSA later. Okay, so this is the graphene oxide, or we call as GOSA. And then the last one, we are using the BPSA. Okay, BPSA, the highest modulation depth is about 8%. Okay, so as you can see, the same configuration, just change the saturable absorber. I change saturable absorber to the back phosphorus saturable absorber with X% modulation depth. Okay, okay, so this is the optical spectrum. Okay, during this time we are able to use 3D. Okay, before this only 2D, right? Okay, okay, and then this is optical spectrum. So it measured by from 2 minutes until 8 minutes. Actually more than that. However, I just captured the optical spectrum on for 8 minutes only. Okay, so it's stable enough for 5 lasing. Okay, so this is the dark pass. Actually it going down. Okay, dari below than zero, it going the the pulse is going down, okay, and then this is the input power from 90 to 220. So as you can see, 90 milliwatt is already show the dark pulse, and then going to 130 milliwatt, the dark pulse is still stable, and 220 the dark pulse is already shaking. Okay, more than 20, I think 230 milliwatts is already disappear. Okay, so by right 90 milliwatts, the dark pulse is already appear. Okay, and then again, this is the autocorrector measurement that we got to catch. Okay, uh, as you can see, normally autocorrector, they will show one lasing at the middle at zero position. Like CNT, we go to CNT. Okay, this is autocorrector measurement. As you can see, one lasing at zero position. Okay, for 770 femtosecond. However, in dark pulse, we got like this. One lasing appear high at the negative 37 picosecond, okay, delay time, and there are some like a small uh, pulse, okay, at the 37 picosecond, okay, and then I have to make a research back to previous dark pulse. Most of them cannot get any kind of measurement from autocorrector. Only one on 2002 by Sylvester, if I'm not mistaken, he got the same autocorrector, left and right, okay, for dark pulse. So when I perform the theory, it's because of the phase actually. When the bright pulse is collapsed, so it forced to appear the lasing at the right and left. Actually, the right is the highest one. Okay. I don't want to show the calculation, but this is the reason. When bright in the middle is collapsed, so it forced to be appear at the left side actually, and the right side is we won't consider. Okay, but it's appear. So I just want to show you the real autocorrector. Okay, and then this is the RF spectrum. As you can see, this is a very high OSNR 74.2 dB. Okay, so compared to previously GOSA is only 43, but using black phosphorus with deep modulation about 8%, so uh, it produce very high stability dark pulse, okay, with 74.2 decibel. So for summary, I'm quite fast, right? So summary, okay. On 1973, Hasagawa and Teppert found dark solitone in theoretical, okay, theoretical only on 1973. However, after 14 years ago, 14 years after that, in 1987, Emplit et al. Demonstrated experimentally dark solitone. Okay, and then uh, and then 15 years after that, okay, then this is that I told you this is very difficult to produce. So it took 14 years gap and then 15 years gap, okay, to produce the dark pulse 5 laser. So Sylvester demonstrated experimentally with autocorrection measurement, so with left and right position. So he is the one who showed the same autocorrector measurement with me. Okay, so the theory behind that uh, in number six later. Okay, so and then started from 2002, and then it started the various dark pulse development. However, no autocorrection measurement is performed, is demonstrated due to nanosecond pulse width. Okay, uh, I think I can get the autocorrector measurement because in picosecond. Okay, normally because the limitation of the pulse width. Okay, and then so there are two theory. First is nonlinear Schrodinger equation, okay, and LSE. So for this NLSE is not quite very well, cannot, it's not fit with my result because uh, it said it's on how to say anomalous and okay, that one is very difficult to explain. I will say this is not fit to my calculation. The calculation is not fit into my result. However, the theory number 2, complex Ginsburg-Landau equation, that one is fit to my result. Okay, with the autocorrector right and left and right side. Okay. And then beside that, we also cannot create the strong dark pass. The same configuration, we change the zirconia fiber to erbium-doped fiber, we cannot create the dark pass. And also we also take the bismuth thulium-doped fiber, still cannot create the dark pass in the same configuration. Okay, and then the second one, we remove the single mode fiber 200 meter, and then it's not perform the strong dark pass. Okay, it's perform the switchable only. Okay, switchable and not very stable the dark pass. Okay, so and then the last one, using low modulation depth of saturable absorber like CNT, that one cannot perform the strong dark pass fiber laser. Okay, so as conclusion, dark pass were successfully demonstrated experimentally using the first one, when we are using zirconia fiber. Zirconia fiber, as I told you, it produces very high erbium concentration doping with 4000 ppm and high birefringence of fiber. So this birefringence is very important because it's also known as a double refraction into two different direction of the fiber. Okay, double refraction with two different direction. So that means it multiply the refraction, so it become more useful and coherent laser light inside the fiber. And then the second one, we need additional 200 single mode fiber because this one is to increase the optical non-linearity in the experiment configuration. Okay, the non-linearity, as I said, to make strong frequency, polarization and phase in the configuration. And then the last one, we need the strong saturable absorber with the large modulation depth, as I said before. Say a single wall CNT only 2.8%. Okay, that one is only perform soliton mode lock bright pass. GOSA 3.5, they perform it show the dark pass, however not very neat, clean. And then when we put BPSA, black phosphorus, with 8%, it perform very neat and clean dark pass. Okay, so because this large modulation depth cause a strong pulse shape and allow safe starting, okay, either in bright or dark pass fiber laser. Okay, thank you, that's all. Any question right now?
Dr. Arni, we have a lot of questions.
Wow.
I hope you are ready. So the first one from our audience is from Norita. Miss Norita, is the modulation depth affect the formation of dark pulse? I think you just answered this. If yes, what is the minimum value of the modulation depth required to achieve dark pulse?
I think inside of it, I share the result. Okay, here modulation depth here is we try CNT at about 2.8. Okay, cannot perform the dark pass, but when GOSA 3.5, it can perform the dark pass. Okay, so try to make it about at about 3.5 or above for modulation depth.
So according to literature, that is the case as well, around 3% for modulation depth.
Yes, 3% and above with strong
with
fiber.
strong EDF zirconia fiber. Okay. And then the next question is from Mr. Muhammad Yusuf or Dr. Muhammad Yusuf, I'm not sure. How do you adjust the polarization controller to get the desired output?
Okay, to be honest, for this, when I'm using strong black phosphorus saturable absorber, I don't need the polarization controller. Okay, I put that polarization which intend to control the polarization, right? But when I put the the black phosphorus, it's already appear the dark pass. Okay, but it very used for NPR. Okay, NPR, as I said before, we are not using saturable absorber, right? Okay,
Mhm.
so this polarization control is play uh, com- uh, important things to play the rotation polarization inside the configuration to create the dark pass.
Okay, so what you're saying is if you're using a material-based SA,
Mm-hmm.
the polarization controller is not needed lah.
Yes.
Okay, okay. Okay, next question. Um, from Mr. Amir Murad. Hi, doctor. How can we interpret dark pulse obtained with BPSA and not with CNT with similar cavity configuration? How can we interpret dark pulse obtained with BPSA and not with CNT with similar configuration? Is Mr. Amir Murad here? Can you clarify what the question means?
Yes. What the question? What do you mean by is it
Okay.
the dark pass uh the dark pass train here?
Hello, doctor.
Hello. Hi.
Hello, doctor. Actually, I'm just gonna confuse that when we use just zirconia doped fiber other than erbium-doped fiber, so we are going to just shift the dispersion like we got 80 dB.
What? Adan? Dr. Amir, can you
Can you
repeat your
repeat it?
question?
Yeah, can you repeat again? Sorry.
Hello, you can you hello?
Yeah,
Yes,
yes, yes.
can hear you now. Okay, go on again.
Um, what? What? Confused what?
Amir, I think your microphone is not working. Can you type the question again? Elaborate a little bit on your question, on what you were confused about, and I can read that for you. Okay. So I'm going to move on to the next question, and we will go back to Mr. Amir's question in a bit. Okay. The next one is what is the normal peak power for dark and bright pulse?
Peak power.
Mhm.
Okay. Again, peak power is depend on the saturable absorber also, the cavity. Either it's strong in the strong non-linearity and strong birefringence. Okay, so for example here, CNT for bright pass, 97 milliwatt is already enough to create the soliton. Okay, and for NPR, 70 milliwatt. Okay, but not soliton, just single ledging here, but it's already enough to create bright and dark pass, switchable bright and dark pass. Okay, and for GOSA, 54 milliwatt. Okay, see the strong saturable absorber will self starting at the lower pump power at 45 milliwatt is already appear the ledging and dark pass. Okay.
Muhammad Yusuf, did that answer your question? Is that okay?
Okay.
Yes. Okay. Right. Thank you. Okay. Next question from Norita again. Since dark pulse is very difficult to be generated, how about the repeatability? Is
Oh,
it repeatable? Yeah.
yeah, yes, it repeatable. For my with using these three things. This Zirconia fiber, single mode fiber, 200 meter, and strong saturable absorber. Even we repeat again and again, still the dark pass will appear. Okay,
Okay. That's good.
I can perform it again and again by using these three components.
Okay. So next question. Also the RF spectrum with 74.2 dB stability illustrates side bands. How can we differentiate it from noise like pulse?
sideband.
Yeah, your RF spectrum with 74.2 dB yang
Okay.
okay, this one. So it's saying that there's sidebands in this RF spectrum, and he's asking how do you differentiate from a noise like pulse?
So
NLP.
actually, we perform one single up here, and below one is just CW, continuous wave. Okay, so we this is just normal. This is not considered noise. This is just CW emission. Okay, so we just looking at one single lasing like this, like the small here. Okay.
Okay, so I think this would bring to my question: how do we know that it is actually dark pulse? Is it always accompanied with lasers? I mean, the lasing lines in the OSA spectrum?
No, because first we know this is a dark pulse because it going down. Okay, as you can see, okay, this is the difference between bright pulse and dark pulse. Okay, wait, okay, can you see this one?
Yes,
Okay.
yes.
Bright pulse as you can see, the pulse is going up. Okay, means while the dark pulse it going down. Okay,
Mhm.
you see the difference?
Yeah,
So
but
the reason we know this is dark pulse.
okay. So everything else is the same like bright pulse except for this
Yes,
measurement. So
yes,
this is the only way to know that this is a dark pulse.
yeah. Because the optical spectrum is similar with bright pulse, but the different only this from oscilloscope. This one is we get from oscilloscope.
Oscilloscope, okay.
Yeah.
Okay, so moving on to the next question. I have a very basic question if I can ask. What is the importance of dark pulse? Is your purpose to maximize the dark pulse?
Okay. We as I said before, we have so many application, right? In the military, dermatology, communication, medical, biotechnology, laser application, right? Okay. So this dark pulse has advantages. Okay. It less noise, less interference, and then it has a strong, excellent stability in the presence of noise compared to bright pulse. Okay, so uh, for medical, for example, for medical, we want to cut human body, right? So it must be efficient and sharp enough. So why not we use the efficient laser, the most efficient laser kan, to decrease the percentage of failure, right? So this is we need to improve again and again the dark pulse because um, they are looking this one is uh, much better than bright pulse.
Okay, so the main advantage is efficiency, you would
Yes,
say?
yes. Less noise, less interference, and excellent stability.
Okay.
Okay. However, still ongoing research.
Okay, thank you. Okay, next one. What is the, oh, sorry. I want to ask, does GVD play a role in deciding the formation of dark and bright pulses?
Yes, this question play a very quite important role inside the calculation to prove the theory. Either they are using an LSE or CGLE. Okay, from GVD dispersion, we know that my result is not fit into the NLSE.
Come again? Your equation does not fit?
Yeah, GVD is
Group velocity dispersion.
yes, dispersion, right? Dispersion.
Uh,
So this dispersion is important to identify either it fit in theory 1 or theory 2. Okay, because it's important to make sure our result is not random, right? So it must be tally with certain equation. So with the dispersion, we know the NLSE theory is not fit into our result, but CGLE is fit
mhm.
based on our GVD.
So is dark pulse mainly formed in net anomalous dispersion, normal dispersion, or near zero dispersion? Typically.
Okay. For my dark pass is normal.
Normal dispersion.
Yes.
Okay. Okay, next one. What is the type? There's a lot there. What is the type of fiber sensor that you already work on? As I can see in your biography. Okay, this is not related to the talk, but it's okay.
Fiber sensor. I'm using for water monitoring for seawater level. For heavy chemical parameter in the river, because in Johor we suffer from Sungai Kim Kim. If you know Sungai Kim Kim, so I'm doing right now the sensor to detect the heavy
For
chemical from
instance
the
lah.
river. Mm.
Okay, cool. Okay, where to buy this zirconia fiber? Which company? This is from
No,
Dr.
this one is not commercial fiber. This is homemade fiber from India. So it's still under research, improving. Okay, I think after it, he he confident maybe he will selling.
Okay. Also, the facility is in India. Not, I thought it was in UM. No, it wasn't done in UM.
The MCVD. That one is from India. Yes.
Oh, okay, okay. Okay, next question. What is the orientation of isolator in the experiment setup?
What?
The orientation of isolator.
Isolator orientation for isolator. Go this isolator, right?
Mm-mm.
It's up to what WDM from pump we go the laser we go to WDM, Zirconia, central observer, and going to isolator and go to WDM.
So Dr. Fairuz, the isolator helps to force the propagation of light in clockwise direction. Next question, can you elaborate a bit on CGLE? How does it differ to NLSE? This is from Dr. Fariza.
I'm not put in any calculation here. So the phase, the GVD is fit in. I'm not sure because I did not put any calculation here. I thought it's very complex to explain. Okay.
Maybe Dr. Fariza can take a look at your papers. Do you have that elaboration in your papers?
Not published yet.
Oh, not published yet. Okay. Okay.
Sorry.
We will wait for that.
But it's I calculate and it's okay. But it's not published yet. So be patient, okay?
Okay, soon, inshallah. What is the nonlinear parameter of zirconia fiber? Was it correct? The nonlinear parameter, coefficient code, nonlinear coefficient.
Nonlinear coefficient. Wait, see my thesis here. Yeah. Zirconia. Okay, do you want to see the fabrication and characteristic here? They only give me there.
No characterization on the nonlinear coefficient?
No.
Oh, okay.
I think no. Yes. I think got, but not here.
Okay, so we will wait for that fiber to be commercially available and we will know. Okay, so next question, can we drop cast the material solution directly on fiber ferrule without using a host polymer to make composite material polymer film?
Polymer? I'm not using the polymer.
So it's just the material, right?
Yes, polymer normally for using for sensor, right?
You can have it in SA. So basically you use a scotch tape.
Okay. Okay. No, I'm not using the polymer for SA.
Okay, so how did you put the BP flakes on the fiber ferrule?
Just cut into the small piece. Okay, that one from flake. So if we go to okay like this. Can you see this one?
Oh, you use a tweezer.
Yes.
Oh,
Okay.
okay.
and then by index gel matching gel to glue in the middle of the two pixel.
But index matching gel.
Yeah, it's like a
Oh,
glue.
okay.
Uh,
I hope Dr. Mahmood or Mr. Mahmood is taking note of that. She used an index matching gel after she used the tweezer. Is that right?
yes.
Okay. Okay, I think noted by knowing the nonlinear parameter, you can understand the reason of why you still need the long SMF to get the dark pulse, in my opinion. This is from Dr. Fariza.
Mm.
Because you did mention about SMF contributing to the nonlinear,
Sometimes
right?
when we collaborate with other people, they still hide some of parameter like this.
Oh, okay.
Because yeah, like that.
Okay, so I have another question from Dr. Zuraida. What kind of photo detector do you use before the oscilloscope to detect the RF spectrum?
Mm,
Ingat ke? Ingat.
I don't remember. I'm sorry. I'm just using the available one.
Okay.
But I know high tech photo detector.
High speed?
High speeds
High
because
speed.
before that we have very long time ago we have what a very low speed photo detector, so it
Uh,
cannot detect the dark pulse very neat. Okay, so when we choose to high speed, and then it can
sure.
detect capture the dark pulse.
Okay. Okay, faham. What kind of, sorry, is it direct detection or coherent detector?
Mm,
You know?
coherent detector is what is it? Yeah, Dr. Zuraida. I think direct detection.
Sorry if I can just answer it using audio. It's something like when you can see the mixing of the RF signal in order to see it to see the spectrum away from the DC. Meaning like you can see the spectrum away from the DC point at zero, if you like, in terms of the spectrum analyzer. I mean, you'll be having it at multiple of megahertz per second, third megahertz. Because if it is direct detection, you would see it only at the DC point on the zero axis of the RFSA, if you like, something like that. Because I've seen that you've got several spectrums, kind of like sidebands in the RFSA. So I was wondering whether it is some special kind of detector that you could see the intermodulation detections in a way such that.
I'm not study about that.
It's okay.
Because
It's okay. I'm just wondering. I'm not in the field, but I'm trying to relate with my understanding in terms of the detections when I see the spectrum just now.
actually the side that you see from RF actually this is what I told you. This is like this one, the below one. This is continuous wave emission. So I just make it bigger so it appear like sideband, but actually it's not sideband.
Okay. I see what you mean. Thank you, Dr. Arni.
So thank you, Dr. Nadiah. FS levels.
Are there any more questions from the audience? That was a very fruitful Q&A, I believe. Okay. So I have one more question and maybe we can close the Q&A after that. Kesian Dr. Aini. Okay, so when the bright pulse, sorry, not the bright pulse, when the peak in the middle collapsed, right? You said it break into the left and the right, right? Okay, I don't know what you call it specifically. However, you only considered the left side because that one was like the one with the peak, right? And the other one was like very shallow. So why is that? Why do you only consider one part? Why is the other not considered?
Because okay, like this we are not considered this one because we cannot measure any pulse width from here. There is no width here. It's not
Okay.
going up, right? So here we can measure the pulse width, but the right side cannot. So that's why we just considered the left instead of the right.
So in the literature that you mentioned before, the breakdown was also symmetrical, was it?
Symmetrical.
Sebab yang ni 37 dengan minus 37, right?
Yes.
So symmetrical lah kan? Okay.
Yes.
Okay. That is it from me, and I hope everyone enjoyed our session today. I really enjoyed the discussion and the Q&A, and especially Dr. Arni's talk. I hope we can have Dr. Arni again in the next few years, maybe on something else other than dark pulse. Thank you everyone for joining us. As usual, the recording of this session will be available on YouTube. You can just Google IEEE Photonics Malaysia YouTube, and you will find all the talks that we have recorded there.
Dr. Fairuz, wait, Nadiah, Dr. Nadiah, Dr. Fairuz, the ZER-B, that one is very previous long time ago Zirconia. He did fabricated a lot of Zirconia, but this one is not mine.
Oh.
So it's okay lah. I will ask him what is the nonlinear coefficient for my fiber. Maybe he will will tell me later.
Tinggi juga 14 what? Okay.
Yes.
Yours is much more higher maybe.
Yes, much more higher I think.
Okay. Thank you everyone, and I'll see you in the next session.
Nadiah, take photos.
Oh yeah, forgot. We need to take photo. Can we have everyone to turn on their video cam? What do you call it? Camera? Yasmin boleh tolong tak?
Boleh.
Okay. But I can't view it.
Hai Kak Ira.
Thank you, Arni. Nice presentation.
Thank you.
Yeah, we're still waiting for some of the participants to turn on their video. Okay, ambil yang ada lah. All right, smile. 1, 2, 3. Okay, thank you everyone.
Thank you. Bye-bye everyone.
Bye.
See you in the next one.
Kak Ira datang. Johor.
Inshallah.
Dr. Siti pun ada. Dr. Siti, thank you for coming.
Thank you, Arni.
Assalamualaikum.